Hey guys, here we are. We're going to talk about continuous functions, not continuous functions, the definition of continuity, among other things. So thanks for tuning in. Let's just jump right in. A continuous function you could think of as a function where you don't have to lift your pencil off the paper when you're drawing it. And so some classic continuous functions, you got your sine or your cosine curve. You got a polynomial, whether it's a cubic, parabola, that type of thing. You got your absolute value, like V shape, something like that. All sorts of things. Not continuous, there's a few different ones. Here's tangent. Tangent's got an asymptote. Any function that has a hole in it, it's called a hole. It's also called a removable discontinuity. Right, this first one's an asymptote. And another one that comes up sometimes when you have a piecewise function is maybe you have a jump. This is actually called the jump discontinuity. And a lot of this stuff has just different behavior. Sometimes these have limits. This is a limit. The limit exists even though there's a hole. But right here at C, the limit doesn't exist. And so we're going to be talking about continuous functions, not continuous, and in the context of limits. All right. So definition. And if I go too quick, feel free to pause this and jot it down. This is a definition you want to know. It says that function f, generic function f, is continuous at a point. We're talking about at a specific point. X equals c if and only if the following are met. So f of c has to exist. So if you have a hole, at c, this fails step one. There's a hole there. It doesn't exist. If there's an asymptote at C, so C is at the origin here, that doesn't exist either. Those values, f of C does not exist. That fails number one. Number two, the limit has to exist at C. And so if you look back at this first example, the limit exists here, but the value doesn't. And so in order for it to be continuous at a point, the value has to exist, the limit has to exist, and they have to be equal to each other. And so, for example, if you had something like this with a value up here. So technically f of c exists, and technically the limit exists. But the limit is this value, and f of c is this value, and then step three is it fails. That criteria is not met. And so in order for an entire function to be continuous and not just the point, you'd have to have continuity at every single point on the function. So if I look back to this, even though that tangent is continuous on this interval, you can't say the entire function is continuous because every asymptote that you get to has a problem. All right, another quick definition is a cusp. A cusp is a point on the graph where the function is continuous, but the derivative is discontinuous. So it's easier to describe a function, a cusp, with a picture. Anything that has a sharp point. So this right here is a cusp. Another kind of weird one, if it's more pointy like this, this would be a cusp. An absolute value, for instance, what the absolute value of x. That looks like this. A little sloppy, sorry about that. It's supposed to be pointy right here. There's a cusp at 0. And so we're going to come back to this a lot because there's some interesting features when we start talking about the derivative. that is the chapter 3 content. But just know that a cusp is going to be unique because the function is continuous there. You can draw it without lifting up your pen. But the derivative, when we start taking those, the derivative is going to be discontinuous, which is kind of a unique feature of cusps. All right, property of equal left and right limits. I'll just go through this real quick. What this says is that if the limit as x approaches c from the left equals the limit as x approaches c from the right, then the limit as x approaches c of f exists. So in just a simple picture, in order for the limit to exist, you have to have the function, approaching the same thing from both sides. If you have one-sided limits that do not approach the same value, then you cannot say that the limit exists at c. And so if you have a picture, it's easy to wrap your head around. All right, and again, if I'm moving quick, it's just to keep the video short, but you can always pause it. Example, determine if the function is continuous or the function definition changes. So the function definition is this idea of we're defining this piecewise function, and we really care about what's happening at -1, on the graph. And we talked a little bit today in class about how to graph these, and the idea is 5x plus 3. If I do that separately, 5x plus 3 has an intercept at 3 and passes through here. And then x cubed plus 5, as an intercept at 5, and then you have this cubic shape. But the idea here is if we're graphing the piecewise function, the idea is we want the cubic shape, but that cubic shape is going to stop when we get to -1. And we're going to have the line that includes all the values to the left. Whoop, shouldn't have used that less than or equal. To the left of -1. So if I want to know what the value is leading up to at -1, I could plug that in here, and I get a -5 plus 3, which is a -2. But because it's not included, meaning I'm using this symbol, I have to use an open circle, and the line would come down like this. And so I put the graph in here just as a good reminder, just to make sure you remember how to do it. But you don't have to graph this to answer the question. If it says determine if the function is continuous, all you really need to do is compare the two pieces at the value that matters. All we really care about is what's going on at x equals -1. And so I did it with the first piece, and I got a -2. And if I do it with the second piece, x cubed, it'd be -2 cubed plus 5. That's going to be, did I do that right? No. Why did I put -2 in there? Sorry. -1 cubed plus 5. That's going to equal 4, which is this guy up here that I wrote. Now, since -2, that's this, and 4 are not equal, the conclusion is they're not continuous. So to determine if a piecewise function is continuous at the interesting point, right, the point where the function definition changes, you basically have to evaluate each piece at the point. So, cool. All right, last example. And again, give you a chance. It says, find the value of k that will make the function continuous, then sketch the graph. Think about this for a second, guys. Pause it. Pause the video. So you probably hit play, or maybe you never paused it, but it'd be nice if you thought about this before just watching my solution. If I were in class, I'd have you, partner up with someone, think about it, talk about it, think about how you could solve this. So the idea here, if you want the solution and the spoiler, is I want to know when this piece is equal to this piece. If I want it to be continuous, these need to be equal at the point where the definition changes, right? That -1 is the most important point in this graph. So I want to know, when is this line equal to this parabola, and I want them to be equal. And so I really want to know what's happening when x is -1. And if I simplify this, I'm going to get -k plus 5 equals k. And if I solve for k, I get 5 over 2. Or 2.5 if you prefer. So what in the world did I just find? Because a lot of times we get on these journeys and then we forget what we even found. So what we found is the value of k that will force these two to touch at x equals -1. To finish this up, if you want to verify it, try plugging into your calculator. Hopefully you can do it by hand. It's not too bad. But if you actually graph this now and write 5 over 2x plus 5 when x is less than -1, and you wrote this as 5/2 x squared when x is greater than or equal to -1, what you would have, and this is just a rough sketch, but you would have a line, and when it comes into -1, it's going to come in perfectly and touch this parabola. 5/2 x squared is just your classic x squared. The 5/2, if you forgot what this coefficient does, is it makes the parabola skinnier or wider, depending on the coefficient. Maybe punch it into Desmos, see what comes up, see if you can figure it out and verify it. But trust me, it's right. So, all right, we're trying this from home, so hopefully you viewed it. If you have questions, you can put them in the comments section if you want. Bring them to class tomorrow, but I appreciate your guys' willingness to watch. Hope you have a good night, and I'll see you soon.